There's Professor Barak Kol, who's from the Hebrew University in Jerusalem in theoretical physics. We met through the email, like a lot of us. He was looked at a paper that Rick and I wrote about 8 years ago. So that's how we started interacting, and I suggested he talk here. So look forward to hearing about it. So thank you, Barak.
Great. Thank you for the introduction.
Oh, wait. I'm supposed to tell everybody to turn their microphones off and their cameras, right? Okay, thank you.
Okay, great. So good morning, everyone. Thank you, Richard, and the organizers for the invitation to speak here. I'm a newcomer to the three-body problem, and it is great to see here people that have read their papers. Montgomery and Meckel I've read, and I've read some work by Shensinel and others. So really thank you for joining. So the topic is natural dynamical reduction of the three-body problem. I will explain in a moment what I mean by dynamical reduction and what I mean by natural. And it's based on a paper that was posted to the archive. Usually I invite questions during the talk, but this talk appears that it's going to be rather tight. So if it can wait to the end, it might be better. So first, I'll introduce myself since I don't know many of you. So my background is in theoretical physics. I work in fundamental laws of nature, quantum field theory, Einstein's gravity. I was educated in string theory. I did my PhD at Stanford in 1998, postdocs at Tel Aviv University and the Princeton Institute for Advanced Studies. And since 2002, I've been at the Hebrew University of Jerusalem. I got to the three-body problem somewhat by chance. I saw a great paper by my colleague Stone and by Lee in 2019, and then it got me really interested and excited. The paper was very interesting, and that's when I started working on the problem. In a sense, this is the second subject that I work on in the three-body problem. You'll see in a moment. However, this is not my first adventure in mathematics. I have some background in mathematics, and in particular, in 1997, I defined an object that I call the PQ web, which is rather close or essentially the same as the definition of a tropical curve, which is given later by Michalkin, and that's the opening of the subject of tropical geometry, which has rather developed and flourished. And Michalkin was generous to acknowledge the relation of the two. Okay, so I'll start by briefly telling you what the talk is about, and then we'll have a more orderly outline, and I'll go one by one, point by point. So the three-body problem needs little introduction. We have three bodies with masses M1, M2, M3, locations R1, R2, R3. There are some forces that we can take to be the Newtonian gravity forces, but for this talk, it doesn't matter actually. As long as the potential depends only on the interparticle distances, that would be good enough for the purposes of this talk. And we are asking, well,
Barak, let me interrupt. Yes. I'm not seeing any slides. Are you showing slides yet?
Uh-oh. Thank you. Just a minute. Did you see the first slide?
I can see the slides.
All right, I'll see how to change my screen. I'm not seeing them. Okay, go ahead. Just go ahead.
So
I have a
some people can see and some don't. Maybe someone can explain how to add the slides to so that Richard can watch it.
I figured it out. There's a little blue button on the right. Thank you.
Great. Yes,
All right.
yes. That's what I pressed. Okay, so can you see now the three-body problem figure?
Yes.
Great. So I'm just briefly reminding the problem. And I just mentioned that the force can be Newtonian gravity, but it can be any other force, such as electricity, springs, whatever. Generally, we want to give an initial conditions to solve the problem. But here we'll ask a different question. We'll ask whether we can improve the formulation rather than solve the problem. Later, we'll also see that solving should be asked somewhat differently than the way I just asked. Okay, so what do I mean by a dynamical reduction, by a different formulation? I mean that I want to simplify the dynamics or the formulation of the equations of motion to a choice of variables, actually fewer variables. Why fewer than the original ones? Originally, we had 9 positions and 9 velocities. Well, because we have conserved quantities which limit us to some submanifold of phase space. Example for dynamical reduction is that any oscillator with a more than 1 degree of freedom can be decoupled into a set of decoupled one-dimensional oscillators, or that any central force problem can be decoupled into the radial motion, and then you solve for the theta coordinate, for the angular coordinate. These examples are not exactly the same as what we'll see later, but those familiar with these examples will have some idea what I mean by dynamical reduction. Later, we'll see what happens in the three-body problem, and we'll see some more motivation. So here is a schematic view of the decomposition that we're going to have of this dynamical reduction. We'll see that the system will be decomposed into 2 systems. We have 3 bodies. The 3 bodies, their positions, always define a plane. So we can follow the motion of this plane. This is what we see on the left-hand side. And then within the plane, And then within the plane, we can follow the motion of the 3 bodies within the plane. And that's depicted on the right-hand side by this 3-dimensional geometry space that we will explain later. So a point in the right-hand side geometry space tells us a shape of a triangle, shape and size of the triangle that is defined by the 3 bodies. And then it moves in a space where it feels some potential-derived force and some magnetic derived force. And the blue arrows are supposed to depict the magnetic field that lives in this geometry space. And the variables on their left-hand side are the angular momentum vector J. Let's see if I can highlight it. Yes. Okay, these are the variables over here. And over here, the variables are the 3 position vectors. I will call it G vector, the geometry space. And the conjugate or the associated velocities. So this is just to give us some schematic view of the bottom line of the talk, but I definitely did not explain everything. Now I'm going to go step by step, and I'll try to give a rather reasonable amount of detail of how we get from the original picture, the original variables of the positions, to this decomposition into 2 sets of variables, which are not decoupled. They are coupled. They are coupled because the moments of inertia of this rigid body on the left, so the plane moving through space, behaves as a rigid body, though it's not rigid. The moments of inertia depend on the positions of the point over here. Okay, so altogether, we have a point moving on the right-hand side and a vector J of constant magnitude rotating over here, describing the rotation of the plane. If I know that I didn't explain everything, but if something that I did explain is not clear, this is a good time to ask. Okay, so I'll proceed and we'll go now step by step. So the outline is now I'm going to discuss some background. Why did I reach this question to start with? And then I'll describe the process whereby I arrived at this reduction. So the process will have 4 steps. First, we will cover translations and the new variable, a new complex vector called W. Then we'll discuss planar reductions and the angular velocity omega. Then in-plane rotations and the geometry space vector G. And finally, we will do a Legendre transform to angular momentum and replace the angular velocity omega by the angular momentum J. So finally, our variables are going to be J and G. And then we'll end with a summary of the formulation and discuss some applications. Okay, so let's start with some background. So as we know, the three-body problem holds a central position in the development of all of science. It strongly affected the development of mechanics, of perturbation theory, of analytical mechanics, of chaos. Topology, modern topology was defined by Poincaré around the same time that he was working on the problem, and he was influenced by that. There are astrophysical applications. When we discuss the dynamics of stars in star clusters, these are dense environments of stars, then we have many binary stars, and every once in a while, a third star, a tertiary, approaches the binary, and then for a while, they behave as a three-body system. However, this is never stable for the generic case when the masses are comparable, the non-hierarchical case, and it will finally decay. But studying three-body dynamics allows us to understand the population and the statistics of star clusters. It's also very important for understanding the sources for gravitational waves. Gravitational waves are created by tight binaries of black holes or neutron stars, and it's a current puzzle how these tight binaries were created. And one of the 2 leading explanations for the mechanism to generate these tight binaries has to do with three-body interactions, a third star interacting with this binary and making it tight. So we'll go quickly over the beginnings. Newton was the first to define the problem, but for the specific case of the moon. Then Lagrange in 1772 worked on the general three-body problem, and he presented a very different formulation. Rather than looking at the position vectors, he looked at the position at the edge sizes or distances, RAB squared. And following that, he had to add some more variables. But these are really, this is really the first step to the formulation that we will see today. And for a while, people were looking for a general solution, just like Newton was able to solve in general the two-body problem. But then, of course, Poincaré in 1890 discovered chaos. He discovered, or it's believed, that no general or deterministic solution is available in closed form. And there's an interesting question, how to interpret the series, the power series of Sundman, but I will ignore that for now. But this broke the clockwork universe paradigm. So people before that, like Laplace, thought that if you know all the initial conditions and you know the forces, you can predict the future arbitrarily well. But since we always know the initial conditions to some limited accuracy, in practice, we cannot predict the future more than some typical time. So it's impossible to find the general solution, but once people started doing computer simulations, and I want to show you now a computer simulation, they understood what is the correct question. So I'll briefly show you now computer simulation. Let's see if this will work for us. Oops, screen share has ended. No, that wasn't my intention. Application window. Okay, can you see the video window now?
Yes.
Yes. Yes.
Great. So we see here a simulation by Alessandro Trani, I think he's here with us as well, from Japan. And we see here a binary system on the left and a tertiary approaching it. And then we'll see some long-term interaction. It's not the typical one, but it's something that does happen. So we'll see a lot of close encounters, but then you see it's very random. Time here is not uniform. And then it goes like this for quite a while. Each time two of them get into a close encounter, then two others. But the system is unstable. Finally, it will disintegrate. One of them, you cannot predict which one because you see that it's so random, but one of them will finally be shot out of the system. And I will skip ahead. Here we will see the first ejection in a moment. Here, the yellow one is ejected. However, this is not an escape because the velocity is below the escape velocity and it falls back. See, it falls back and now everything starts again. Well, here's immediately another ejection, but this one is not terminal either. It's not an escape either. And now this thing will go on for a while, this sequence of intermediate ejections, then three-body ergodic-like motion or random-like motion, and finally there will be one ejection which will be so strong it will be above the escape velocity and the system will disintegrate forever. But that would happen much, much longer, so I'll skip over there. Here is, I think, the last moment. We see here it's coming back from an excursion, and this is probably the last ejection, which is terminal, and now they will never fall back together. Okay, so this is how computers can allow us to understand the system in a way which was really impossible to people before the computers became available. Okay, now I'll go back to the talk. Okay, I hope you can see now back the PDF after this brief intermission to see the video.
Yes.
Wonderful. So, so now we have to change our objective. Instead of seeking a general solution, but the most we can hope for, since the motion is so random, is to seek a statistical solution. What is that? What does that mean? That means given initial conditions, we're not going to predict the future, but we're going to predict the probabilities for various possible outcomes. The probability distribution for various possible outcomes. In particular, since the system decays, we can ask what are going to be the final states, what are going to be the distribution probability for the final states. So that has, since the 70s, that was understood to be the correct question to ask about the three-body problem. And following the work of Stone and Lee, I proposed a flux-based theory, which proposes an exact reduction of the statistical solution. Okay, so the statistical solution is not stated, but it is reduced. In what way? The decay rate, which is the quantity of interest, is written as a product of two quantities. The asymptotic phase volume flux, or phase space flux, which goes to infinity, describing a binary separating far away from a tertiary. So that's rather easy to calculate because it's not really three-body, it's really decoupled. This is given in closed form. So this part is known. However, this other function, E, emissivity of U, where U are the outcome parameters, this is unknown. Okay, so we write it as a function of two, as a product of two functions. The first one is known, So this is the reduction. The second one, for instance, can be measured in a different way. So this is ongoing work now. And together, this product will give us the total probability distribution, or decay rate, differential decay rate. This is normalized by a quantity which is independent of U, and it's called the regularized phase volume. It's not related to the regularization of collisions. It's related to making the phase volume of the system finite, because a priori, it looks like it's infinite. So we use the word regularization here in the meaning of being finite. And this regularized phase volume is what led me to the current study. Let me explain why. Okay, so this is just to give you some background. So that was my previous work on the reduction of the statistical solution through a Fluxbased theory. And the total phase volume, given energy, total energy, and total angular momentum, is defined as an integral over all of phase space with delta functions for energy, for angular momentum, for linear momentum, and for the center of mass position. So we have here 18 variables to integrate over, and we found that we can integrate analytically all but 2 of the variables. Okay, so that led me to think that this simplification of the integrals might hint that the system has a simplified formulation using those variables of the integration. And indeed, this expectation was realized in this work. So now I'll try to show you what we did. But this was the reason, or the motivation, why we started this work, because we were able to change variables in this integral and perform analytically many integration over many of these variables. Okay? Okay. So let's proceed now. Oops. I'll go over the previous work, and I'll immediately start with the first mathematical point. It's very simple, but I think it's important. So we have 3 positions, but then we want them to satisfy the center of mass constraint. So here is the center of mass constraint. And the question is, can we choose 2 free variables rather than 3 constraint variables? Is there some canonical way to do it? That would help us. In the 2-body system, there is a way to do it. We simply take the difference R1 minus R2, the difference between the 2 positions. And this is almost invariant. The only thing is that if I change the labels 1 and 2, it changes by sign. But otherwise, it's very reasonable to take that as a coordinate, and that's what we always do. And we can write the 2-body motion in terms of this relative separation R. What can we do in the case of the 3-body? Well, in the case of the 3-body, we have 3 relative separations, R1, 2. Okay, the relative separation is defined like so, R2, 3, and R3, 1. And they're not independent, of course. Their sum, if you plug the definition, is of course 0. So what can we do? How can we make a symmetric, natural choice among these 3 variables? So popular choices are non-symmetric. For instance, in the planetary limit, where one mass is much larger than the other 2, then we take the distances from the bigger mass, R1, 2 and R2, 3. Or in the lunar or hierarchical limit, when 2 bodies, say the moon and the earth, are much closer than the third one, say the sun, then we take the distances to be the interbinary distance and the distance between the center of mass of the binary and the third one. But as you can see, this is not symmetrical between 1, 2, and 3 in the general case. In the non-hierarchical case, when the distances are non-hierarchical and the masses are non-hierarchical. And a way out is suggested by a rather different mathematical question, solving the cubic, or the cubic polynomial. So let's review that quickly. So Lagrange, by Lagrange's time, of course, the solution to the cubic was known, but he suggested a new way to do it. So here is the cubic, and he suggested defining 3 variables, S0, S1, and S2, which are linear combination of the x's, where x1, x2, x3 are the roots of the equation. S0 by definition is already known. It's minus b over a, known in terms of the coefficients of the equations. And S1 and S2 have the property, where eta is the cubic root of unity. So it's a complex number. And S1 and S2 have nice transformation properties. And in particular, S1 cube and S2 cube are invariant under cyclic permutations and are exchanged by exchanges of 1 and 2. So this is Lagrange theory, which is the precursor of Galois theory. And so we first solve a quadratic for S1 cube and S2 cube, then we take cube roots. So we find all the s's, and then we invert the linear system of equations and we find the x's. Okay, so the main point is this definition of S1. Now we're going to imitate it instead of a cubic equation for the three-body problem. So the number 3 is there. So here is the answer to our first question. How are we going to find independent, natural, canonical way to choose variables? We're going to define a vector, complex vector W as so. So we take the 3 vectors and we combine them using a cubic root of unity. Only now I use J as the complex unit rather than I, because I will use it later to complexify the XY plane. So we'll have 2 kinds of complex units in a moment. So for now, we're using J. So you can see that we started with 3 vectors, and now we have a complex vector, which is like 2 vectors. So we have the right amount of degrees of freedom. There are no relations, no redundancy. It is invariant under translations. If we add a constant to all the positions, W does not change, just like R1 minus R2 in the 2-body case. And it also has nice transformation properties under permutations. Under cyclic permutations, you just multiply by a phase in J. And under exchange of 2 and 3, you just take the complex conjugate. Okay? So we're going to use this complex vector W. This was the first step out of 4. But this is an important step that so far I think was missing. Now we're going to do the planar reduction and introduce the angular velocity. So here is the picture. So the idea is, I hinted at it already before. We divide the specification of the configuration into 2 parts. First, we specify the plane, or the normal to the plane, and then we specify coordinates in the plane. So in the plane, it's just 2-dimensional vectors rather than 3-dimensional vectors. So we need to know the orientation of the plane and 3 2-dimensional vectors. The dynamics of the plane will turn out to be just like a rigid body, the rotations of a rigid body, only here it will be non-rigid. So it will be slightly different. And the motion within the plane will be related, in a moment we'll see, to the quotient C2 over U1, which is related to the shape sphere, which you are familiar with. So here is a second question. When we look at the motion of this rigid body, can we define a Lagrangian or a Hamiltonian? I call this motion potential. This is not a standard name. For a rigid body. So the answer is yes. I wasn't familiar with this. Before that, here is the kinetic energy written in terms of omegas. So I first call them omega tilde as the angular velocities, and I is the moment of inertia tensor, the standard definition. It depends on the positions. There's also a term linear in omega, which multiplies a certain angular momentum, which depends on the motion within the plane. And then there is a term which depends only on the motion within the plane. So all these 3 functions depend on W. Oops. Okay, so can we find a Lagrangian or Hamiltonian for this? Well, if we just use these potential energies as Lagrangian, then we don't get the correct equations of motion if we just apply the Euler-Lagrange equations. So actually, I found the answer myself and only later discovered that Poincaré had already found it in 1901, but still it was fun. And it was later discussed by Arnold in the 60s and more recently by Marsden, Holm, and others. So let me tell you it really briefly how it works. So we want to discuss a Lagrangian which depends on some generalized coordinates q, but rather than depending on the general velocities q dot I, it depends on some linear combination of them, VA. In our case, these are the angular velocities. And these are some linear combination of the q dot i's with coefficients which depend on q. So it's a change of basis, a local change of basis or a change of frame. And then the Euler-Lagrange equations need to be supplemented by one extra term, which is this term. So we have here the standard term d by dt of the conjugate momentum. Here we have the standard term derivative with respect to coordinates. But here we need to add a term which has velocities times momenta, sometimes coefficients, which I think can be called torsion coefficients and are defined as follows. If you take the betas and you make one forms out of them, and you take the external derivatives of these betas, then you can write them, these are two forms, and you can write them as a linear combination of beta wedge beta, and the coefficients here are these c's which enter the equations of motion. Okay, so this can be solved rather neatly. All you need to do is to express the kinetic energy in terms of omega, and then there is a method to get the equations of motion also for the omega variables. So most physicists don't learn it yet during their undergraduate curriculum, but perhaps they should. Okay, so this was step 2. Step 3 now, we have to take care of the rotations within the plane. So far we took care of the orientation of the plane. And here we encounter our third and last question that I wanted to highlight. How does the overall rotation in the plane, which I call psi, change from being a cyclic coordinate in the two-dimensional case? So it's a coordinate which it does not appear directly in the Lagrangian, and there is an associated conserved current, the conserved quantity, the angular momentum, and it changes to a non-cyclic quantity when we do three-dimensional problem. I'll try to, we'll see how this question is answered, but at first, something a bit strange appears to be going on here. And we have a hint. The hint is that the rotation along the axis, which is normal to the plane, z axis is normal to the momentary or instantaneous plane, and that rotation is the same as changing psi. So we already have here a redundancy, or what we call in physics a gauge. So we have some redundancy in the description. We have 2 degrees of freedom which describe the same thing. We can rotate the 3 bodies within the plane either by increasing psi or by adding to omega tilde z. In a moment we'll see a bit better how it works. So the next step is, once we've reduced it from 3 dimensions to the plane to 2 dimensions, then W's are now 2-dimensional. So the W is a 2-dimensional complex vector, so it has 4 quantities. And I'm going to package these 4 quantities for real components a bit differently. So I'm going to define a bicomplex number by this expression, which means simply that the x component of W becomes W1 plus W3J, a complex number, and then the Y component of W becomes a second, two more components. Sorry about this. So now we have as promised, we have two imaginary units. We have J, which was related to permutation of the three objects, of the three bodies, S3, and we have I, which is related to plane rotations. So a phase e to the I phi is a rotation within the plane. And they are both imaginary units, so both of them satisfy I squared equals J squared equals -1. It should be -1. It's not easy for me to change. Let's see, maybe I can change it. No, it doesn't look very nicely. Okay, so here we see some minus, okay. And in addition, I and J commute. So Ij equals Ji. So these are independent and commuting imaginary units. So I call this object is called a bicomplex number because, well, it has both I and J, so it's bicomplex. The next step is to perform spherical or to move to spherical or Hopf coordinates. So we can decompose W into 4 coordinates: R, theta, phi, R, theta, phi, and here I use a coordinate that I call psi plus. It is related to another coordinate called psi, but for now we'll need only psi plus. And these two basis vectors, E right and E left, are related to the equilateral triangles of unit size, the right one, the right-handed one, and the left-handed one. And they're given as bicomplex numbers by these interesting expressions, which happen to be zero divisors from the algebraic point of view, but I will not dwell on it now. So this transforms from the 4 W's, the 4 components of W, W1, 2, 3, and 4, to these radial spherical coordinates R and the 3 angles. And the first thing we find that the Lagrangian depends not on omega and psi dot separately, but only on their combination as such. And that leads us to define our final angular velocity vector omega as this sum. So this is how the redundancy gets solved. This is the gauge invariant quantity, if you like, or a kind of a Higgs mechanism. And yeah, I will not add much to this. But now if we're interested to mod out or to take a quotient by plane rotations, that's the same as multiplying by a phase with respect to I, e to the I phi. And it is known how to take this quotient. This quotient is taken by using the Pauli matrices. So this is known since Stokes, the Poincaré sphere, they discovered it in optics, then Pauli and Bloch discovered it in quantum mechanics, then Hopf discovered it, well, before Bloch, but after Pauli, in the mathematics of vibrations of the S3 sphere. And later it was used in the context of the three-body system by Lemaitre, though not explicitly, and later more naturally and explicitly by Meckel and Montgomery. So what we do here is that we define 3 real numbers that I call the vector G, and they characterize the shape of the triangle, the shape and size of a triangle. So a point in this G space tells us exactly the size and shape, or what I call the geometry, for a lack of a better word, of the triangle. It doesn't tell me the rotation within the plane, nor the orientation of the plane. Okay. And here is a picture of shape sphere, which I understand you're familiar with. So on the North Pole, we have the right hand equilateral triangle. On the South Pole, we have the left hand, or the left pole, the left hand equilateral triangle. Then we have the equator of the collinear, or of the collinear configurations. If you like, you can call them ecliptic configurations, because one of them just masks the other two from each other. And over this equator, there are three special points, the coincidence point, which are equally spaced. So this is very similar to the Poincaré sphere in optics and in quantum mechanics. Only here there is a permutation of three symmetries. So they are equally spaced, and there is a natural action of the S3, the permutation on three objects. So this same object was defined by Meckel and Montgomery, and they christened it or gave it the name shape sphere. Only they had to reach it through some Mobius transformations, and while here using the W variables, we get there rather naturally without trying too hard, I would say. That's the way at least I think about it. Finally, the last step, the fourth and last step, is we're going to change from the angular velocity to angular momenta. And the reason is that angular momentum is conserved, so that would be easier. Though this angular momentum is not going to be in the inertial frame or the lead frame, but it's going to be in the body frame. So this is a frame of axes which is attached to the plane. So this goes as usual. We define J to be the conjugate to omega, and here by taking a derivative with respect to a vector, I mean the gradient. And so we get angular momentum, that's the interpretation in the body frame. And then we perform the Legendre transform, and we have to replace everywhere omega by J. And the novelty is that due to this non-coordinate basis and the method of Poincaré, the angular momenta are no longer Poisson commuting, but rather you have to impose some Poisson, non-zero Poisson brackets between these angular momenta. And this is also standard for rigid body rotators in the body frame, though it's not always taught in this way. So that's it. These are all the components. Now we can go over to the summary of the formulation and see what we have here, and hopefully the dust will settle down and the picture will clarify. Okay, so we had these four steps, and let's see what we finally have. So we finally have, again, these two parts, the part with the J, which describes the motion of the plane, and the part with G, which describes a point moving in this geometry space. And if we forget about the radial angle, the radial coordinate, then we get a sphere, which is the shape sphere. And here is the formulation. This motion potential, which is intermediate between a Lagrangian and a Hamiltonian, it's a Hamiltonian with respect to J, but Lagrangian with respect to G, will be a sum of three quantities. The first ordered by powers of J. So the first quantity is independent of J. We have here a metric or a kinetic term over geometry space. Unless you ask me, I will not even describe all the definitions, but you can see that I have here some radial coordinate dot squared, and we have some kinetic term in the spherical or angular directions. And there's also the potential term. If it is Newtonian gravity, then we should write the distances in terms of the r theta phi coordinates, and that's possible. So this is the term L0, independent of J. Then there is a term linear in J, so it's proportional to J, and it's proportional to this quantity Lg, which is some kind of general velocities. You see here phi dot and theta dot. That's related to a vector potential or a connection in mathematical terms. And we can take the field strength of this connection, or in physics jargon, the magnetic two-form, and we get this outgoing, we get a two-form which is tangent to the, or proportional to the two-form on the sphere. It has no radial component. So it's only along the sphere. So physically, I think we can call it a radial magnetic field if we take the, I don't know, the Poincaré, the Hodge dual of it. then we get something which is sort of radial. So that's the magnetic field associated with this motion in the geometry space. And it has a monopole charge, or in mathematics we would call it a Chern charge, sitting at the origin. Finally, there is L2, which describes terms j squared over I. So here we have j squared over I, and here we have j squared, and here I inverted I explicitly so it can be explained. And altogether, this term has two purposes. When you write equations of motion with respect to j, it generates the rigid body equations of motion. Whereas there is also dependence on g, because the i's depend on g, on the geometry space variables. And then you also get the fictitious forces acting in a rotating frame in the geometry space. And in particular, we can interpret these quantities as a centrifugal potential. Again, if you'll ask me, I can explain a bit more, but this is something that we're used to from the two-body problem, and here we can make similar definition in the three-body problem. So the equations of motion are gotten in the standard way. For the Hamiltonian quantities, they're gotten by Poisson brackets, and for the Lagrange quantities, or the G variables, they're gotten through Euler-Lagrange equations. And that's it. That's a summary of the formulation. So in closing, I think I have one more slide or two more slides for applications. So maybe I'll just do that, and then I'd be very happy if there are any questions. Okay? So two kinds of applications I want to mention: applications to the statistical solution and applications to the exact solution. So to the statistical solution, that goes back to this regularized phase volume that I mentioned before. Okay, the figure here is incomplete, but if you remember this pipe joint that we saw, where did we see it? Over here. So we're trying to kind of compute the volume of this pipe joint. But it's infinite, obviously. However, far away it goes to a cylinder. So we're going to subtract from it kind of straight cylinders, and the difference between this pipe joint and the flat cylinders, that's a schematic view, but it's almost correct, that would be finite. So that would allow us to define this regularized phase volume, which will set the scale for the decay time. That will tell us how much time does it take for the system to break up, to disintegrate, to decay. Okay, so thanks to the new variables, we would be able to compute this regularized phase volume, and this is work in progress, as I mentioned. So originally I mentioned this as motivation, but we can also think about it in hindsight as an application. Okay, we're going to be able to learn something about the statistical solution. Secondly, the new variables allow us to see in new light the known central configurations of the three-body system. So the Euler and especially the Lagrange solutions. So it gives you a, perhaps you can call it a different derivation of this equilibria. And more interestingly, it also allows you to perform a stability analysis. And the reason that it's a bit easier in this case is that instead of thinking about uniformly rotating solutions for these central configurations, we think about them here as static solutions. So the North Pole and the South Pole are the two Lagrange points, for example, and there are static points in these variables in geometry space or on the shape sphere. So it's easier to do stability analysis around an equilibrium point relative to doing stability analysis around a rotating, a moving solution. But of course, in the end, it's equivalent. So it's, if you like, two different points of view, maybe it has some advantage. So that's the second application that I wanted to mention to the derivation and stability of the uniformly rotating solutions, which are part of the central configurations of the system. So great. So I think we roughly made it in time. Let's see. I think that was almost the last transparency. So I just want to remind you what were the novelties here. There were many ingredients. Many of them existed in the previous literature, like in Meckel and Montgomery, and especially in Lemaitre. But the definition of the complex vector W, later the bicomplex W, that was novel. And formulation in terms of J, the angular momentum vector, that was also novel. And here again, we have this picture. And I thank you very much for your attention.
Well, thank you. Thanks a lot for the talk. It was interesting. Are there questions or comments?
Yeah, I would like to ask a question.
Please.
When you introduced your variable W, I think, at the beginning of the talk, right? I think you wanted to deal with the translations.
Yes.
That was the idea, right? And then you mentioned those relations that Lagrange introduced to study the solutions of the cubic, right? To represent
yes.
them. Well, that can be generalized to higher degrees, right? I mean, you have the so-called Lagrange resolvents, right? I think that's how they're called. So I think that part of the construction can be done for more bodies. I mean, I don't know if you thought about that.
Yes, thank you, Eduardo, for this question. This is by definition an excellent question because there is a chapter in the paper which I didn't mention, which addresses it at least partially. Okay, so we know how to solve not only the cubic but also the quartic. Similarly, we can define a generalization of the W to the four-body problem. So not to any number of bodies, but at least for the four-body problem, there is a natural generalization, and it is mentioned in the paper just the same way that you do for polynomials. So you have x1 plus x2 minus x3 minus x4. So you have two of them with pluses and two of them with minuses, but there are three ways of choosing 2 out of 4. So there are three quantities that you can define in this way, and you can do the thing, just replace the x's, the solutions, with the vectors R1, R2, R3, R4. So I have here some issue with using my tablet, but I hope it's clear enough what I'm trying to convey. Yeah, great. So you can do something similar for the four-body problem. I did it just for the W variables. I didn't complete it yet for the other steps which were done here, but at least this step was generalized already. And for the other ones, it doesn't work in polynomials, so I don't think that it has to work for the n-body problem.
Yeah, I understand that, yes. Thanks a lot. It was a very nice talk. Thanks.
Thank you.
I guess I'm going to chime in for a second about Eduardo's question. Why don't you just take the nth roots of unity and do R1 plus omega R2 plus omega squared R3, etc. You know, up to omega to the n minus 1 R to R.
Right. I wasn't sure. Was that Richard asking?
Yes.
Okay, just to be sure. Yes, thank you for the question. Yeah, that's a very good question again. I did think about it. I believe this does not work. And why? Oh, hi. Hey, there's a young mathematician there as well. So I think that transforms very nicely with respect to cyclic permutations, the suggestion that you just made. But what about other permutations? You want it to transform nicely under all permutations.
I see. Okay.
For the 3 and 4 body problem, it still works nicely for other kinds of permutations, not only cyclic ones. But for 5 and higher, this, I think, will not work any longer. So I don't know. I don't know if there is a generalization, but I don't see one right now. I didn't see one so far.
More questions?
I think that Shai had a question in the chat.
Jair asks, can the probabilistic approach be used on special cases of the 3-body problem like Sitnikov's or in other directions to many bodies?
Okay. Okay, good. So Sitnikov's problem is the one where we have a binary and then the third guy is moving on the axis of the binary but outside, right?
Yeah, up and down.
So that case, due to the high amount of symmetry of the initial conditions, the motion is not quite random as we saw in the video. So the statistical method works well for a motion which is truly ergodic, that you have these close encounters and then you cannot anticipate what will happen afterwards. And I know I don't remember how does the motion look in the Sitnikov case. I know there are also some ergodic-like things going on over there. So my guess is that maybe one could use a statistical approach there, but it would have to be formulated a bit differently because we would be looking not at the most general solution, but rather at some special. So that would be some very high codimension submanifold in a phase space, and you would have to do some kind of statistical physics on this submanifold. So I haven't attempted it, and it could very well be interesting. I really don't know. And there was also a second question about the generalization of the statistical approach to more bodies. I think the fair answer is that I didn't consider it. Of course, physically, it is less likely to have a 4-body interaction than 3-body. So on physical grounds, 2-body systems are common in space, and then once in a while, a third guy will approach them. So having 3-body interactions is something not uncommon, but 4 bodies would be more uncommon, more rare. Well, I don't know. I'm open to discussion on the 4 and higher body case, the statistical theory. I just didn't give it much thought so far.
Other questions?
I was wondering about the collinear configurations where none of the vectors kind of make sense. It looks like you ended up with something in the kinetic energy similar to Lemaitre with the area of the triangle in the denominator. So it's probably a singularity of your system, the reduced system.
I think it is not a singularity, but let's see. Okay, good question. First, very nice to meet you, Eric.
Yeah, likewise. I enjoyed your talk.
And now let me see if I can. I'll try to here. Okay, so here is the shape sphere, and this plane of collinearity is the equatorial plane. And you're asking what happens as we go through this equatorial plane. So if one uses only the edge lengths as the dynamical variable. This was done, for instance, by Murnaghan. Then you have a symmetric formulation, but it definitely becomes singular in the equatorial case. I think the nice thing about these coordinates is that they don't become singular. We can at least, let's see it, at least some of the terms don't become singular. So I usually think about, or I look at L0.
Yeah, the
So
L0 is fine. It was L1.
Right.
Oh, no.
L2. I think you were worried about L1 or L2. So L0 is fine, right? There is no problem there.
Yeah, it's the kinetic term in the involving.
Right. So now about L1. So L1, I think there is no issue either. There is no delta over here. But in L2, there is a delta. There is a delta over here related to L2, but there is also this I bar. So this is the inverse matrix of the moments of inertia. Of course, when it's collinear, the moment of inertia matrix is singular. So yeah, that's a good question that I should think about what I have. Well, of course, the others were good also, but this one bothers me. Well, what could happen? I mean,
I think it's just the ice skater effect, you know, with the ice skater pulling in the arms and spinning infinitely fast. I mean, it's just it may be impossible to get rid of. I'm not sure.
You understand?
But we know.
If you have the three collinear, there's no resistance to spinning a line. That's what Rick's talking about, the ice skater effect.
But I think we can agree that physically there is no singularity. I mean, especially Richard, I think he studied a lot these syzygies or these collinear situations. And we know that every motion goes through infinitely many such configurations. And nothing bad happens there as far as I...
Yeah, but
right?
that's for zero angular momentum. And your term L2 is all about the angular momentum. Right? I mean,
okay, that's for zero angular momentum. What about non-zero angular momentum? Don't we have these collinear passes through collinear as well?
Yeah, I think it's due to the reduction, maybe. The singularity comes from the reduction, maybe trying to use that angle as a coordinate.
That's my guess. My guess is that when you think about it in the original variables or of R1, R2, R3, okay, consider the planar problem. I think in the planar problem, it's quite clear that you will have collinearities all the time. And nothing strange is supposed to happen there, even if you have non-zero angular momentum. Okay, for the planar problem with non-zero angular momentum, it's all moving in the plane. The three of them are moving, and it's a codimension one event to have collinearity, right? So it happens every once in a while. And in the original variables, there's nothing strange happening there at all. Only in the reduced variables, it appears to be strange. So it could be, one way to have this happening is that the I bar over here in the delta could have canceling singularities. So this is one possibility that I would guess, but this is just a wild speculation at this point. So I think it's an interesting question, and my guess is that it's not a true singularity of the system of the equations of motion, but one has to investigate it a bit further.
And let me ask while you have that slide up, what if you are interested in the purely planar system? Which variable do you set J3 to be 0? What do you do?
Great. Yes, so this is a limit that is very nice to take, because in this limit, the motion of the plane completely disappears, and we are left only with geometry space. So in that case, we have just an angular momentum which is normal to the plane. So the J vector has only one component, J3, while J1 and J2 vanish.
I
Okay?
see. So you set J1 and J2 to be 0. Okay.
Right. And then J3 is automatically conserved. Previously, only the magnitude of J was conserved. Now J3 is conserved, and it becomes it really looks like a centrifugal potential in the planar case. So you have your some constant divided by a function of the geometry space variables.
Okay. All
Okay.
I just have a comment in case you didn't know. There's this partial Hamiltonian Lagrangian. People in mechanics sometimes call that the Roofian.
Yes. Yes, I know. Thank you.
Okay. I figured
that's exactly why I started calling it the motion potential instead of calling it a Lagrangian, a Roofian with respect to this, a Roofian with respect to that, a Hamiltonian. We have the same problem in thermodynamics. We have this thermodynamic potential and then do a Legendre transform and get from the energy, we get the free energy or the enthalpy. And then we have their name. We call all of them thermodynamic potentials. So I'm trying to promote this idea. We cannot call it a potential because the potential is already the force potential, but maybe calling it a motion potential is reasonable, but that's already outside of physics, outside of science. That's more into words, which are also important.
And then about your statistical study, have you looked in these chapters of this book by Heggie and Hutt, the million body problem?
Yes, thank you.
Okay.
So the statistical study was very interesting because I did not only get the reduction, let me return to this reduction. We also tested it in experiment. And when we say tested in experiment, we think here of testing against numerical simulations. So we ran millions, well, it wasn't me, it was Alessandro's here in the audience and Viraj and people who are dedicated experts on these numerical simulations. They ran millions of simulations and we collected the statistics. And one thing that we compared were the probabilities for each one of the bodies to be the one that will escape. Okay? For any given initial conditions, it will finally disintegrate, at least in all the cases that we saw with our initial conditions. And then you can ask, what are the odds for each one of the bodies? For instance, if they're all equal mass, then by symmetry, it has to be 1/3, if it is indeed ergodic. And amazingly, that's correct to very good approximation. Then what happens if they're not equal? You can measure the odds and you can compare it to the probabilities that you get by integrating or marginalizing this probability distribution after approximating that you ignore the emissivity because it kind of averages out. So you make one more assumption, you integrate only over the known factor, and you get some very simple formula. And rather amazingly, the data fits to better than 1% over a range of masses. Okay? And that's to date the best or the most precise statistical theory for the three-body problem. To be fair, I have to mention that this success is not yet reproduced for other measurables. So you can also measure what is the average energy of the binary or all kinds of other parameters. And for those, you would need to know more about the emissivity. So for the identity of the escaper, you can turn a blind eye on the emissivity and you get excellent results. And now we're studying what happens for other quantities where we have to, well, measure the emissivity maybe by other terms and then use that and compare. So that's work in progress. But so far we have very encouraging results, kind of experimental theoretical physics or doing experiments with computer. And regarding your question about Heggie and Hutt, I think we're familiar with their works. I haven't personally read it. Maybe Alessandro wants to comment if he's still here. Maybe he read the book. Just in case, you don't have to. But we're familiar with, so there were many works by physicists especially on numerical simulations, starting with Agekian and Anosova in 1967, and then Arseth in Cambridge, and then later the statistical theory of Monahan, today in Australia, but then he was, I think, in Cambridge. So he presented a statistical theory, but that theory was not perfect, and that theory developed until the paper by Lee and Stone, which I mentioned in the beginning of the talk. That was the paper that brought me into the problem, because they achieved some progress in getting closed form expression from this statistical theory. But then I changed the fundamental premises of that theory, the way probabilities are measured. So you get different formulation, different quantities, and you get this very good agreement with simulations. So I answered maybe more than you asked for, but I hope it was relevant. Yeah.
Okay, any more questions? Well,
do we have time?
I have time. I don't know about.
Well, I'm happy to stay with anyone interested, as long as you're interested, either recorded or unrecorded.
Well, I just have one more.
Please.
I'm just wondering about this probability measure. There's a natural measure on if you fix the energy in the angular momentum, you get a natural measure on that integral manifold. But but that's infinite volume probably, or definitely. And so I'm wondering whether your regularized measure has any kind of naturality, dynamical naturality to it. I mean, it is always a problem with these statistical studies that you have an infinite, what's the probability when the whole phase space has infinite volume?
Right. So this was really the deep issue with the statistical theory, all the statistical theory preceding the flux-based one. The preceding theories were, I call them volume-based. So they equated probability with the volume that you just mentioned.
Yeah.
But there is a problem. The volume is infinite, as you just mentioned. So what was the adopted solution? The adopted solution was to cut off the integral at some distance, capital R, known as the strong interaction regime or region, the strong interaction region. And that's some function of the other parameters. And that's a kind of it serves as a cutoff. It makes the probabilities finite, but it has some freedom to it. It is not part of the data. You have some, it's clear that even the closed form solution that was presented by Stone and Lee, R was one of its variables, but R is not part of the data. So how can the solution depend on some arbitrary parameter? I call it spurious parameter. So that was exactly the issue with the previous formulation. So I started by trying to regulate this, trying to send R to infinity. But later I changed to a different approach. And the different approach is that since the system is disintegrating, it's a bit different than a closed system. A closed system has a compact phase space. And then the volume is finite, and then you can define probabilities. Here, it moves for a long time in some bounded region, but finally it moves to infinity. So what we're actually interested in is not the volumes, but the rate at which this volume is flowing out. And this is exactly this flux that I'm talking about. It's your volume flowing out to infinity. There's all the time volume coming in from infinity and volume going out to infinity because of conservation of this volume. And this term over here, the asymptotic flux, is exactly as you go to infinity and you measure the flux. So whereas the volume is infinite, the flux, the rate of change of the volume, is finite and independent of the place where you measure it, in fact. So it's a well-defined finite quantity. So the intuition there is to consider a container. Yes?
Go ahead.
Richard? Okay. The intuition there is to consider a container of gas, but a leaking container. It has a hole in it. And there is some molecule moving inside. Maybe one of the molecules is painted red, so it's moving inside the container. And then you ask, how much time would it take to get out? And the time that it would take to get out is if you measure the flux of the gas out of the small hole, this gives you the rate, the probability rate, the rate per unit time for this specific molecule to leave the vessel. So I think of this as an analog for all of phase space. Yes, the point represents the whole system. This container represents the three-body phase space, and it's moving for a long time in some rather bounded region. We saw all these collisions back and forth, or close encounters, not collisions, of course, but close encounters. And then there is this thing that the point goes out, either far away and falls back, or really to infinity. So I was using this analogy of the leaky container in order to base this flux-based approach. So it's based not on phase space volume, but on the flux of phase volume.
Asking.
Sorry?
The flux is positive, it cancels out. The average flux is 0, yeah?
Well, there is an incoming flux and an outgoing flux.
So you just take the positive, the outgoing part. You just
Yes.
truncate and take the outgoing part. Okay, I understand.
Yes, yes.
Okay.
Exactly. So that's already published. The statistical theory was already on the archive, and it's published by Celestial Mechanics and Dynamical Astronomy. Since you liked it, I can mention that it was rejected by quite a large number of journals before it was accepted, but finally it was accepted.
All right. Well, welcome to our little community here, and thank you for the talk.
Thank you very much for the hospitality. Appreciate it.